In this lesson, we're going to talk about simple harmonic motion. So let's suppose we have a spring, and it's sitting on a frictionless horizontal track. It's at equilibrium, which means there's no force on it. It's just at rest. If we stretch it out to a position, x, so this is a displacement from equilibrium of x, we're going to have a force now. Once it's stretched, it has the spring force, or what's called the restoring force. This is going to be a force to the left, called a restoring force, that tries to get the spring back to equilibrium. Now, if you let go of the spring, it's going to go back to the center. At that point, it has no more restoring force, but it will have inertia. Inertia is the tendency of an object that's in motion to stay in motion. It's also the tendency of an object at rest to stay at rest. So once it's in the center and it's moving, it's going to keep moving because it has inertia. So it's going to go past that equilibrium point to another point over here. It will continue oscillating. So once you pull it, it passes equilibrium, goes to here. Now it has a force restoring it back to the center, goes back to equilibrium, and it continues going back and forth and back and forth. This back and forth repetitive motion is called oscillation. So when we talk about it on a frictionless spring or a pendulum, which we'll talk about today, that's an object that's at the end of a string or a piece of a bar. These oscillations are called simple harmonic motion. That is when we're going to ignore friction, we're going to ignore air resistance, and we're just going to observe this repetitive motion of the objects. So simple harmonic motion is an oscillation about an equilibrium position with a linear restoring force. That means you could graph the force in a linear graph. So a pendulum is a mass, which we call a bob, so it could be just a weight or a mass, hanging from a pivot point, which would be up here, and is connected by a light string or rod, and this is called the arm. Let's say initially we have it hanging straight down in the center right here, and then it's in equilibrium. Then we lift it to an angle theta above the equilibrium. So we lift it up like this. It's going to experience a net force to the left called a restoring force. That's going to go straight along the tangent of the rotation. It's going to try to restore the pendulum to its equilibrium position. When it reaches the center, it'll have no more restoring force because it's in equilibrium, but it will have inertia, just like the spring. It'll continue, because it's in motion, it'll have a tendency to stay in motion. So it'll keep moving, it'll pass equilibrium, it'll go up to this point, it'll come back, and it'll oscillate back and forth and back and forth. It will continue this oscillation or repetitive motion back and forth. So in a spring, we've talked about the restoring force. On your AP equation sheet, we look only at the magnitude of the restoring force. The restoring force actually has a sign, a positive and negative. We're not going to consider it in this class, but we are going to talk about it a little bit today. The force is equal to the K constant times the displacement from equilibrium. So notice that this force is linear. That means as the displacement increases, the force increases at a linear rate. They're directly proportional to each other. So if you could see it on a graph, and now we're looking at the negative part of it. Let's say we displace it to some place past the equilibrium. Our force is actually negative. So here on this graph, we can see if our displacement is a positive x, we have a negative force pulling it back. If I displace it to a negative x, the same position, I have a positive force pulling it back. And this is a linear graph between f and x. Now you can also do a graph of the magnitude of the force and position, and that would look like this. It would have a positive force. But it's important just to know that the relationship between the force and displacement is linear. That means the acceleration of the spring is not constant. The spring has the most acceleration when it is the most stretched out. When it's in the center, it has zero force, so it has no acceleration. And then this acceleration increases as the force increases. Then it decreases, and then it will increase in magnitude. So because the force is equal to mass times acceleration, and mass times acceleration equals the k times x, the acceleration depends on the displacement. So if the displacement is negative, you could have a negative acceleration. You also will have an acceleration that's value will change depending on the x value, so it is not a constant. It depends on the displacement from equilibrium. For a pendulum, getting the restoring force is a little bit more complicated. We're going to do a free body diagram to see the forces that act on the bob. And so here's our free body diagram. If this is our bob, we have a force of tension and we have a force of gravity. In this picture, it's labeled W for weight. So those are my two forces. But we need to break it into x and y components, and we're going to say this is my y-axis and this is my x-axis. So tension is along the y-axis. Weight can be broken into an x component of weight and a y component of weight. And we can see how those forces act. Well, in the y direction, we know that the pendulum is not accelerating upward or downward. So the sum of forces in the y direction is 0. That means the tension equals the W cosine theta. And that's our weight in the y direction. So the only force that's left after the y directions cancel is going to be this W sine theta. And that's the tangential component of weight. The net force, this net force here, is called the restoring force. This is the force that pulls the pendulum back to the center. The restoring force on a pendulum is the tangential component of weight, and it's equal to mg sine theta, or W sine theta, because W is mg. All right, we're going to talk about some properties that we use in harmonic motion. There's general properties of this motion, and we're going to look at the motion in a graph. So if I had a spring that I pull and it goes back and forth and back and forth, I can map over time. So this is a coordinate system that's flipped sideways, just so that you could visualize it with the spring. We have time going down, and the position is x. It's along this axis. Its largest distance that we stretch it to is called a, or amplitude. Amplitude is the maximum distance of the object from its equilibrium position. If there's no friction, the object will oscillate from A to negative A to A to negative A. And if you could see it over time, the graph of its position would look like this. It goes to A, goes to negative A, goes to positive A, goes to negative A. This is where it's crossing the 0 in the middle. And this graph we're going to be using a lot for simple harmonic motion. To help you do that, we're going to actually flip it to look more like a traditional graph. We have time here, and our amplitude is going to be on the x-axis. And over time, our spring position can be seen as what is a cosine graph. We'll talk about that more in another lesson. So the other properties that we talk about with simple harmonic motion besides amplitude are period and frequency. Period is the time it takes to complete one full cycle of motion. So if my spring starts at amplitude A, it passes 0, goes to negative A, passes 0, and comes back to A. This is one full cycle from the same position to the same position. The time that takes is called period. We use a capital T. It's measured in seconds, but it's not the same as time. That's why we distinguish it as a capital T. We also use a term called frequency, and frequency is the number of cycles per second. So if we have, let's say this was over 3 seconds, we have 1 cycle per 3 seconds. So our frequency is related to period, and the relationship is that frequency is 1 over period. The units we use for frequency are hertz, or abbreviated Hz, and 1 hertz is 1 per second, 1 over a second. And this is the equation on your AP Physics 1 equation sheet. The important part you want to see is that period equals 1 over frequency, or frequency is 1 over period. This 2 pi over omega we're going to talk about in the next unit. All right, so we have period and we have frequency for anything in simple harmonic motion. There's also equations for a spring and for a pendulum for how we define their period. The period of a spring on your equation sheet, and it's written as T sub S. So the subscript means it's for spring. The equation is 2 times pi times the square root of the mass on the spring over the spring constant. So this will give you the period of a spring. We can also find the period of a pendulum, which is on the equation sheet, and it's written by subscript p, and it's equal to 2 times pi times the square root of L over G. Now L is this L. It's written as a capital L in this picture, but it's the length of the pendulum arm because the length of the arm does influence the period over G, which is our gravity, 9.8 meters per second squared. So let's do a couple of problems. Let's say we have a pendulum and it's pulled back to position A and released from rest. The bob swings through its usual circular arc, so it's going to go down to C to D and back to A, and it's caught at position C eventually. Let's determine the position where these different properties take place. So where is the force of gravity the greatest? A, B, C, or D? Well, the force of gravity is always downward, and it's always the same. So it's the same on all of them. Where is the restoring force the greatest? That is the force that wants to pull it back to the center. That's going to be the greatest when it's the furthest away from the center. So it'll be at A and D. Where is the speed the greatest? Well, at A and D, it actually comes to rest, just like on a spring, and it reaches its greatest speed at the bottom, at C. Where is the potential energy the greatest? That will be when it is at its highest point, which would be A or D. And where is the kinetic energy the greatest? Well, that's similar to part C. The kinetic energy is where the speed is the greatest, which will be at the bottom at part C. And the total mechanical energy, where is that the greatest? Well, in our simple harmonic motion, we talk about no friction, so no energy is lost. So that means the total mechanical energy will be the same everywhere. All right, here's another question. Let's say the block on the end of a horizontal spring is pulled from equilibrium 0 to A and released. Through what total distance does it travel in one full cycle of its motion? So it's going to go from A, across, back to negative A, back to 0, back to A to make one full cycle. So let's figure out how far it goes. To get to 0, it travels A. To get to negative A, it travels another A. So now we're at 2A. Goes back to 0. Now we're at 3A. Back to its original position. It's traveled 4A as its total distance. And you can see it on the graph. If it started here, it has to travel to 0, to negative A, to 0, to positive A. That's a total distance of 2A to the left and then 2A back of 4A.